Okay, so the two things that we'll be talking about today are a way to describe, how do I put this? Group presentations, which are essentially the way of describing groups based on any arbitrary relations we describe on them. It is extremely useful, but it can be quite bothersome to use sometimes. Nonetheless, it is essentially the reason why computational group theory is such a big part of group theory as it is. Similarly, we will be going through the Todd-Coxeter algorithm, which is a thing in computational group theory, really, because it allows us to calculate cosets of a given subgroup in a group based on only the presentations here, which then is extremely useful for being able to prove that, for example, a group given a bunch of relations is either not trivial, has certain size, etc. So let's start from the beginning. If you may recall, the free group on a set X is written as f of X, and or f subscript X, and it consists of all of it essentially is the group on a given set which only has the rules as the axioms of a group given on it. So for example, if X is the set AB, the free group Fx consists of all words on the alphabet X, where by alphabet I mean that we are treating X as a set of symbols that we will be creating the words out of. In particular, one very important thing here that I will add is that we are also adding inverses as symbols here. So for example, a typical word here would be something like this. And because there are no relations between A and B here, there's no way to actually collapse this into something simpler. Now, a crucial thing that was proven last session that will be the way forward in presentations is the mapping property of the free group. This, when slightly modified, can give an equivalent definition of a free group. So if we look at this directly here, so given a set X, and a group G, any map from F, any map F X to G extends uniquely to a group homomorphism I'm going to label it phi from Fx into G, such that if we have an element x in X, then f of X is equal to phi of X in every single case. There is a rough diagram that we can do here relating to this. So if we have the set X over here, we have Fx over here, and we have G. we can include x into here. We have the map phi, and we have f. The point is that if we go from x to g via f, it is the same situation as if we were going x into f of x through inclusion, and then f of x into g via phi. In more stricter terms, the diagram commutes. Now, what this allows us to do next is there's a very direct consequence of this, which is very nice, and that is all groups are a quotient of a free group. So, the proof of this goes as follows. So we let G be a group. And we let X to be a set that generates G. So X generates G. Via the mapping property of the free group, we have something like this. We have X that we can include into G via some map F. We have the free group on the set X, inclusion here. And we have the map phi into G itself. One thing that I want to stress here is that this can be chained. This gives us a really nice way of describing things. So, if we continue, give me a moment. So we let f from x to g be the inclusion map from x to g. So what we're essentially doing is moving from the set to the group. Same symbol, nothing really happens. But this then extends to a unique homomorphism phi from fx to g. If we use the first isomorphism theorem here, what happens is that we get that f of fx quotient kernel of phi will be isomorphic to image of phi. So all we really need to do now is that we need to show that phi is surjective. If it is surjective, then the image is exactly G. So, let G be in the group G. Then we can express it as G being some product of elements from X, either raised to the power 1, so themselves, or to the power -1, so inverses. So xi in X, and epsilon I in ±1. So, what happens here very directly is phi of those symbols of x1, epsilon 1, x2, epsilon 2, etc., up to xn, epsilon n. Notice that this is in the free group. Via the mapping property, we have that this is equal to f x1. Oh, gods. One moment. To f of x1 to the power of that. What am I saying? Via the mapping property, and via the fact that this is a homomorphism, we can bring phi inside the expression. And then, because this is an extension of f, as defined earlier, we can turn all of that into f. Notice that the exponents here do actually make sense, because we are operating on something within G, which is a group. So now what happens here is that this, because this is an inclusion map, it's exactly the same thing. And we are done, as this is equal to G. Hence, one moment. This works a bit well, a bit better at least. Yeah. Hence, phi is surjective. So, image of phi is exactly G. And we are done. One interesting thing about this proof is that if you notice a bit further up, what we're doing is that we need a set that generates X here, that generates G here, ideally. There are ways to do it that don't require X, where we can set G as the same group, where we can set G as X itself, and this will still work as intended. But this gives us a bit more insight. What happens here is that we can use this sort of situation as an alternate definition of generating a group. So X generates G if and only if the map phi fx into G extended from inclusion f x into G is surjective. I will not prove this directly, because we have already really everything we need for this proof above. What we are essentially proving above is that any symbol inside of G can be expressed using symbols from F, can be expressed as a combination of symbols that would be in the free group on X. And that means that any element in G is some combination of elements and their inverses in X. So we are essentially done. Now, coming towards group presentations themselves. The idea here is that we want to start off with the free group. So for example, the way we would do this is that we want, like, as a very simple example, what we might want to do in that sense is find a way to describe the dihedral group of degree n in a very succinct way, where we have some set of generators X, and we have some relations between them that completely describe the dihedral group. And this is essentially the goal that we're doing, the goal of presentations. The proper definition here is that if we have that G is a group, and actually, let me explain this differently. The presentation X given R yeah, this should be a bit better. Gives a group with a group G with the following being imposed. Our set X generates G, but in addition to that, we have that for all elements of R, let's say R and R is equal to 1 in G. The more direct definition is that the group defined by X given relations R, which, by the way, R is some subset of the free group on X, is equal to the free group on X, quotient, the normal subgroup generated by R. This is usually written like this. There are quite a lot of different notations for this. I've seen, for example, this being written as norm CL of R. And the best way to, and there is an explicit way to describe this, as this is exactly this set of, this is exactly the subgroup that is the set of all conjugates of elements from, actually, this should be W. This is the set of all conjugates of elements in R by words in f of x, in fx. So, Artin gives a very specific example here of the dihedral group. So, for example, the N can be described as the group with two generators xy, where x to the n, y squared, and xy are all equal to 1. Some authors do change the way that relators are written. So for example, what we could have seen written is xn equals y squared is equal to 1. And xy is equal to yx minus 1. This is probably a more familiar way of describing the dihedral group, but this is generally what I've usually seen, and Artin seems to change this a little bit around in the exercises as far as I know. So if you're following that in particular, generally both of these are useful here. Here's the thing. Sure, given a presentation, you get a group. But how do you prove that you actually have the group you want? So for example, it is not very obvious how you would try to form a presentation for Sn, the symmetric group on n elements, very easily. There is a direct way of trying to describe this via transpositions, as any symmetric group is generated by the transpositions in it. So bijective functions which switch to elements and fix all of the others. The thing is, you would have to actually find all of the relations you need. And this is much more difficult. Even in the case of the dihedral group, there might be some extra relation we need, or that the relations that we gave are not enough. So we need to be very careful here with how we are doing this. So, in order to be able to work with everything properly, we will start with another theorem. This is proposition 8.4 of the book, which is the mapping property of quotient groups. So we let G be a group, and N be a normal subgroup of G. We let pi be the natural function from G to G quotient N, i.e. pi of some G is equal to the coset Ng in G quotient N. We then let G into G prime be a homomorphism which, in particular, has N as a subset of the kernel. Then there exists a unique homomorphism here this is denoted f bar, which is from G quotient N into G prime, such that phi bar of pi is equal to f. This can once again be represented in terms of a diagram. So you have G over here. We are mapping into G prime through here. We are mapping into G quotient N over here. We have pi over here. We have f over here into G prime. And over here, we have our f bar. Once again, the diagram commutes, point being, if we go via pi and via f bar, that's the same as going via f. In particular, f bar of a quotient, of a coset inside of our quotient group, is equal to exactly f of a. So the proof here generally goes very similar to the mapping property of the free group. The only thing I would say that is needed, like, the way you would do this is you define the homomorphism as is given here. If you want to check well-definedness, well, this is given to you directly by the fact that the kernel of F contains the normal subgroup N. As this guarantees that two elements are equal, as this guarantees that two elements map to the same thing, if and only if they are in the same coset of the normal subgroup. Actually checking that this is a homomorphism is nearly immediate. Actually checking that this is a homomorphism is also nearly immediate. Because what happens here is that because of the multiplication on cosets, this is exactly that. We can essentially throw the symbols together, but that is exactly f of ab, which then can be broken up into two parts because f is a homomorphism. And because f is a homomorphism and f bar is defined through that, we get our desired result back. The uniqueness part is a little annoying. And if I can see this correctly, yeah. Uniqueness is effectively forced once again by the way that we've defined f bar. Since we want f bar, that was f bar pi equal to f, we need that f bar of pi of some element a, which is f bar an, to be exactly equal to f of a. And this immediately gives uniqueness, because this is the exact definition of our map. So, now we will prove something very nice, and that is that the presentation we gave above for the dihedral group is the exact presentation that we need. This is proposition 8.3. dn is equal to xy, given relations x to the n, y squared, and xy, all being equal to 0. All being equal to 1. So, it was shown much earlier in the book that dn is in fact generated by x and y. Now, we could do this via looking at the symmetric group, and this is what I would personally do here, as there is a decently clear definition of the dihedral group as a subgroup of the symmetric group on n elements. So where we would have xy, x being equal to 1, 2, being equal to the cycle 1, 2 up to n, and y, if I remember correctly, I need to check this because I actually don't remember this. So bear with me for a little bit. Yeah, and y would be equal to 2n, and then from 3 is mapped to n minus 1, and this goes down where we have and this goes down as needed until we hit a point that we cannot. So for example, until we hit 4 over here. Now that we know that this is generated by x and y that satisfy our relations above, we use the mapping property of the free group. Which gives us that there is a homomorphism from X, which here we will just have it be the set XY. This is inclusion. This is also inclusion. This is Fx. And this is some homomorphism phi, which is surjective, importantly, into Dn. Now, via the mapping property of normal subgroups, what am I saying? R must be contained in phi. Well, why is that? Well, all of these relations are satisfied in Dn. So if we have a homomorphism from Fx to Dn, which is a surjective homomorphism, all of that needs to actually work in f of all of that actually needs to be mapped to 1 by phi. However, now we use the mapping property of normal subgroups. Where
sorry, that reads R must be contained in the kernel of phi?
In the kernel of phi, yes, thank you. That is an important thing to say. Yeah. So what happens now is we can use the mapping property of normal subgroups instead as follows. So we let n be the normal subgroup generated by our relations. Then what we can do is that, again, with the diagrams, because this is honestly the best way to view things a lot of the time. We have f of x over here. We have our homomorphism phi into Dn. We have the map onto the quotient fx quotient n. And then we have a unique homomorphism into Dn, which commutes like so. So, now the goal is that we need to prove that phi bar is bijective. So, notice that phi by itself is surjective. As x being the set xy generates Dn. But that implies that phi bar also must be surjective. This is because that if we have something in, like directly, if we have A in the n, then there exists some, let's say, k in fx such that phi of k is equal to A. But then this is equal to phi bar of pi of k. And we are done, as pi of k directly gives us what we need here. Now, injectivity is a little bit funnier here. In particular, we first notice that f of n has all of the relations in R. So x to the n equals 1, y squared equals 1, and xy equals 1 hold there as kernel as big N is equal to the normal subgroup generated by R. So, given some coset, let's say W n in F quotient n, we can rearrange it into x to the I n times y to the j n, which is equal to x to the I y to the j n. Now, why is that? The reasoning here is effectively the same as trying to find the normal way of rearranging things in the dihedral group. So for example, if we have in any case of some, let's say, Wn in F quotient n, where W is equal to, I don't know, x to the, for example, x squared, y, x squared, etc. What we can do is use the relations here very directly. So let's say we have x. This is x squared n, y n, x squared n, and then times. Since those relations work in F quotient n as previously, yx squared will be then the same as x squared n, that's x squared n, times, we throw that onto the other side, and this turns into x to the minus 2n, yn, which is then equal to yn, because these two cancel out as inverses. Generally, this is what we're doing here, except instead of x and y in the dihedral group specifically, we are working over cosets. So nothing new really happens here. Hence, phi bar is injective, as in particular in this case, what happens here is... Give me a moment. What happens here is since we have a general form for this should be from 0 actually. Since we have a general form of elements of f quotient n, and the size of dn is known to be 2n, notice that the size of f quotient n can also be up to 2n. This is specifically because we have n possibilities to choose. We have n minus 1, actually, possibilities to choose for I, and we have 2 possibilities for j. And because we have, and because this, like this means that this has at most this many elements, but Dn has 2n elements. And since we are surjective, this has to be equal to 2n instead. And we are done. Now, there is one more thing I want to talk about here, and it is that in terms of presentations like so, what if you want a group that is explicitly abelian? Well, there is a direct way of doing this. Let's define the commutator of 2 elements in a group as the following expression: x to the minus 1, y minus 1, xy. The point is that if x and y commute inside of a group, then this is equal to 1. We move x past y to the minus 1, I have x minus 1x, y minus 1y, and these collapse to 1. This is generally a really quick way of doing this, and for example, there is a proposition, and there is a direct proposition here proving this. So this proposition 8.8, let G, x given R, be a group with generating set x and relations R. If R includes our commutator xy for all x and y inside of the generating set x, then G is abelian. The calculation here is very direct inside of G, because what happens is that if xy, x minus 1, y minus 1, xy is equal to 1, what happens is that we can take xy equals yx very directly by looking at the inverse of the left side with the inverses. The proper proof of this also needs to consider specifically words. So, in this case, if we have two words, v equals, let's say, w1, w2 up to wn, and a second word v, which is v1, v2, vn, where all vi and all wi and vi are an x union x minus 1, then wv is equal to w1, w2, etc. wn. Actually, this should be m because we need to be careful. Those words may not be the same size. v2 up to vn. We can push this past wm. Then we can push w2 past wm. vn, the same thing. And we keep going with this. We're essentially pushing letters around according to the rule above. And that is the entire proof of this. This can be done by induction, but I don't think that is very insightful at the moment. Now, group presentations are an important topic in general, but there are a few things that make them annoying to deal with a lot of the time. Like, for example, let's say you have some group, any kind of presentation at all. How do you go about proving that any given two words are equal inside of G? This is something called the word problem for a group, and it is generally actually undecidable. There are no algorithms that solve this in general for groups. And this is one of the easier ones. What if we have two groups with two different presentations and we need to prove that they are equal? Once again, the general way of doing this is very hard, and there is no algorithm that does this automatically. If we don't really have enough time to do this in the session, but if you want a very direct way of seeing how you would go about doing this, it is via Tietze transformations. Tietze transformations essentially allow you to formalize the way you can manipulate presentations. They formalize adding and removing a generator, and they formalize adding and removing a relation in a trivial way. Similarly, we might ask a similar question about conjugation here. Is there an element x such that we can conjugate conjugate w by it to get to v? This is a harder question than the word problem, so things get very annoying. And in fact, there are actually very small groups you can get which have undecidable word problem. I will post this in chat very quickly. And this contains a direct example of a group with a finite presentation and of a finite presentation which has unsolvable word problem. For the people watching the video, This is a paper by Donald J. Collins. A simple presentation of a group with unsolvable word problem. In this case, this is available on Project Euclid for free, as far as I know. Now, I think it would be useful to take a break, as I need to prepare for the second part of this, as the Coxeter algorithm is quite a doozy for me. I am not good at this, I will say that, but I will do my best to explain here. So, we'll take a quick 5-minute break, and we'll be back afterwards.
Sounds great. Stand up, stretch, and we'll see you at the top of the hour.
Okay.
Right, folks. Are we going on to the next page?
Yeah.
Excellent. Okay, let me do a quick reset.
Mm-hmm.
Is your zoom level at 100%?
Oh, it is currently.
Great, that's great. All right.
Okay, found your cursor. There we go.
Yeah, it took me a minute to get there. All right, I think we are ready to go.
Mm-hmm. Mm-hmm. Uh-huh. So, the Tod-Coxeter algorithm is a very nice way of trying to enumerate all cosets of a group given its presentations. If I can very quickly my desk one moment. Okay. This needs to be here. Discord doesn't like working with things, it seems. I love UI problems.
Often the case.
Mm-hmm.
Often the case.
There we go. So, oh, let's do this. The point is that given a group X and relations R, and a subgroup H of G, generated by some Y, which is a subset of G, we want to find all cosets AH, where A is in G. The way we do this explicitly is by working in the symmetric group. This is a little bit funny as to how this works, but generally, the point is that we are looking at the general point is that we look at exactly how all of the relations work. An explicit example given by the book that I will be using a lot is the following. XYZ as generators, relations x cubed equals 1, y squared equals 1, z squared equals 1, and xyz being equal to 1, with our subgroup being generated by z. So, the general idea of the algorithm is as follows. So in our case, XYZ being the being the generators of our original group are permutations. On the set of on the set of cosets that's important. On the set of cosets, I will be denoting this G quotient H, despite the fact that this does not give a quotient group. Part 2, we need that all of the relations must operate trivially. So for example, if something is equal to 1 in the group, it has to be 1 here as well. Additionally, because we are working with the action of a symmetric group on the set of cosets, generators of H must fix the coset H. Because, well, H, the coset, for example, in this case, HZ, or ZH, is only the subgroup H, as subgroups are closed under multiplication. And in addition, the last part, which is not as important as the rest, but it does appear implicitly a lot. Their operation on cosets is transitive, meaning the orbit of every element is the entire set of cosets. So we can go from one element to the other in any way. Well, sorry, I'm misremembering things. If I am understanding it correctly, give me a moment. Yeah, the orbit of an element is of an element in the group itself. It is all of the ways that we can actually get. It is all of the cosets that we can get using a permutation here. But because it is transitive, we only have one orbit, which is everything. Now, continuing. The point is that this is actually enough to give us everything. So, first of all, what we will do in our example explicitly, and this is where things get a little dicey in terms of notation, we will be denoting cosets as numbers. And in particular, we'll have H1, meaning 1 and G, being denoted as just 1. So, the general way this will work is we first look through how all of our relators actually act on things. So, we know that 1x, well, we don't know what 1x would be right now. So we assign it a new index. Let's guess that it isn't 1. So we set it to 2. What is 2x in this case? Well, we once again don't know. The only relation that we have that is related to x only is that x cubed is 1. So 2x, let's say we assign this a new index 3. But 3x is equal to 2x squared, which is equal to 1x cubed, which is then equal to 1, as the action of x cubed must be trivial. Usually, we will denote this using a table, as follows. So 1 x applied gives 2, x applied again gives 3, x applied again gives 1. The relator is at the top as x, x, and x again. Now, we can keep going. We don't know the action of y on 1 yet. We have no extra information. So let's set it to some new coset 4. However, we do know that y squared has to operate trivially, as it is a trivial operator in this case, as it is a relator. It is a relation that is equal to 1. So we get this. And similarly, we can sum this up as a table. Now we keep going through x. Now we keep going through x, y, z. Well, we know that 1x is equal to 2. And we know that, but we don't know 2y yet. All we have for y are its actions on 1 and 4. So let's say this is 5. Because x, y, z has to be trivial, we need to set 5z equals 1. And we do x, y, z, table. Actually, this doesn't look that well. Let's do this. 1, 2, 5, and 1 again. So this gives us effectively everything in terms of what we can get directly from the relators. Now what we will do is create a bigger table using rule 1, i.e. that the operation of the group has to be a permutation. So we will be working on all of the sets that we will be working on all cosets that we can. So we know that x gets us from 1 to 2, from 2 to 3, and then back to 1. But because we have a permutation, this immediately gives us the rest of the results here. 1, 2, 3, 1, 2, 3, 1, 2, and 3, 1, 2, 3. Now, there is a bit of deduction we can actually do in terms of y. If we go back up to here, one z has to be equal to 1, as z is a generator of the subgroup that we are trying to find all of the cosets over. But those two means that z is equal to 1. What am I saying? That 1 is equal to 5. But that then means that 2y is equal to 1. But again, earlier, with y going from 1 to 4, and 4y going to 1, gives us that 2 is equal to 4. And we don't need either 4 or 5 at all. So, let's continue the game of writing everything down. 1 from y goes to 2, then goes back to 1. 2 goes to 1 and then to 2. But we don't know how this will work on 3 yet. So, let's not write it down yet. Now, z has to fix 1. And that is all we know right now. So, this is what we'll write down here. The last bit of the table will be relating to x, y, z. Where we know the following. Now that x sends 1 to 2, y has to send 2 to 1, and z has to send 1 to 1. 2 has to be sent by x to 3, but we don't know how y acts on 3 right now. So the rest has to be left. So the rest over here has to be left completely empty. Also, that little part doesn't need to be there. Also, I am horrible at drawing, it seems. Now, 3 by x has to go to 1. Y, if we go back to the left, we have that it goes to 2. And z, as a result, has to move 2 to 3. So far, we have that x moves 1 to 2, 2 to 3, and 3 to 1. Y moves 1 to 2. And z moves 2 to 3. The thing here... Yeah, we have that 2z is equal to 3. But that means that 2z is equal to 3 over here, and 3 moves, and z has to move 3 back to 2. And then similarly here we have 3 to 3 instead. If we move back to y, because this has to operate trivially, we need to have that 3y is equal to 1. If I am remembering correct. No. I am not remembering correctly, in fact. That is a bad thing. We have that 3 is sent to 2. So y has to be trivial here, which means that 3y is equal to 3. So I write that in. And now we have the entire table filled in, and this gives us exactly these permutations. Through this, we can determine a homomorphism from G into the symmetric group on 3 elements. This, in particular, funnily enough, generates S3. So this has to be surjective at minimum. So, well, this has to be surjective at minimum. It is in fact bijective. It is kind of an annoying situation of how this works. In general, this is quite a bit of work. We've done a lot of deductive things here in order to get here. But ultimately what this proves very nicely, we have that there are three indices. So we have that there are 3 cosets. But that gives us that the index of H and G is equal to 3. But via Lagrange's theorem, we have that the order of G is equal to the index of H and G times H times the size of H. But the size of H, because H is generated by Z, is exactly 2. So there's 3 times 2, and we have 6. So we know the order of G. And that implies that we in fact have an isomorphism, because the order of S3 is in fact 6. A quick question to everyone else. Would you like me to go through a different example, or would you like me to go through the proper proof of how everything works here?
maybe as people are thinking about this, I have a question about this example.
Mm-hmm.
This f that you've constructed here, or that we've claimed to be here,
Yeah.
no, that's a construction. Um, is that f going from G mod H to S3?
Uh,
Or does it matter? Can you just say?
if I am understanding this correctly, this has to go. This has to be a isomorphism from G2 S3 in particular. Because the way this works is that S3, in this case, what we're trying to do is determine a symmetric group which acts on the cosets of H in G. But G itself also acts like this. Like, we have a natural action of G on the cosets, which is via right multiplication or left multiplication, whichever one you like more. And this exactly gives you the same results. The only real thing that we have done here in relation to the symmetric group and why we are why this is represented in this way is that the indices that we are using, 1, 2, 3, can be interpreted as elements of the symmetric group.
Right.
And that gives everything.
Okay. Okay. I think I'm satisfied.
Okay.
We have a no preference in chat, so I think it's up to you.
Okay. I will go through one more example just to show how things can collapse very quickly to much simpler situations. This time, we will be working over G equal, which is generated by x and y, but we have x cubed, y cubed, and yx y squared x being equal to 1. With H being the subgroup generated by y, which is equal to 1y y squared. So, let's start with working through all of the relators. 1x, we don't know the action here, so it goes to 2. 2x, we don't know again, so we go to 3. 3x, then it has to go to 1, because this is applying x 3 times. Continuing, we can look at... give me a moment. Continuing. We can look at y. We similarly don't know how y acts on 1, so let's call this 4. 4y, let's call this 5. And 5y has to be 1, because once again, y cubed here is equal to 1. Lastly, we have the last bit that is a bit more complicated. 1y has to be equal to 4, as earlier. Continuing, we don't know 4x. Actually, sorry, I completely forgot about a thing, and this is why I don't like using this algorithm. Y is a generator of H, so it must fix 1. So nothing really happens here. So instead, 1y is equal to 1 in the second part. 1x has to go to 2. Now, we do not know how y acts on 2. So let's say 2y is equal to 3, and then 3y is equal to 4. But then 4x has to be equal to 1. So the full table will look as follows. We look at the first bit. I will write down everything, but I will be a little bit careful about this because there's a lot of things here. So we have x's, which we had 2, 3, 1 over here. Then this has to be 3, 1, 2. And then this has to be 3, 1, 2, 3. We know that y fixes 1, so let's write that down for now. Now we need to deal with y, x. Give me a moment. This will be y, x, y, y, and x again. Now, we can actually simplify this. We know that y has order 3 here. So y squared is equal to y to the minus 1. So y fixes 1. X goes to x pushes 1 to 2. We have set y minus 1 to be 4 through these two bits here. But x has to return it to 1. So immediately we have an action of 4 of x on 4 itself, which means it has to go to 1. Similarly, we can fill in the rest of this. This is 4. This is 1. This is 1, and this 2. And then at the 4-bit, we have 4. We don't know how 4 has to actually go here, but we know that x to the 4x has to be 1. We don't know what the little bit here is, so it is still a bit annoying. Give me a moment. I think I confused myself. I am going to very quickly erase this because this should be only y minus 1. 2y minus 1 equal 4. Because now it actually makes sense. Let's see. So, first of all, 4x is equal to 1. But also, we have that 3x is equal to 1. So 3 equals 4. And we can proceed to erase a little bit from here. We don't need the entire 4 row. And everywhere that we mentioned 4, we can write down 3. But that means that 2 goes to 3 here. Wait, no, sorry. That means that here we have that 2 y inverse is equal to 3, which is the same as 3y is equal to 2. So you can write this part over here. Now, notice that we also have, from earlier, if I am seeing this correctly, that 2y has to be equal to 3. But also 3y has to be equal to 2. So this means that 2y squared is equal to 3y squared. 2y squared is equal to 2, and 3y squared is equal to 3. But since y cubed is equal to 1 in our original group, 2y cubed has to be equal to 3. But that is already equal to 2, so 2 is equal to 3. So once again, we can completely erase the 3 row and replace all mentions of 3's with 2's. But that now means that y fixes 2. So the entire table is filled in. Give me a moment. So, there is one more thing that we can notice here. If you look at the third relator, the weirdly long one, yx, y inverse x, we must have the 2x is equal to 1. But over there, 2x is also equal to 2. So combining those, 1 is equal to 2. But that means we have only one coset, which is h. But if there is only one coset, we know that cosets partition a group. So h is equal to g. Which is very funny, because that means that if g is equal to h, we automatically have that, since h is a cyclic group generated by y, which has elements 1, y, and y squared, g is isomorphic to the cyclic group of order 3, and we are done. Relations in general, you need to be very careful of those. If you add too many, or if they interact too much, you might collapse to the trivial group, so things get very funny. Luckily, there is no such thing as a conflicting set of relations. Worst case scenario, you get the trivial group again, and everything becomes completely useless in some way. But at the same time, it could be extremely useful knowledge in the other case. So, the proof that this algorithm works is quite technical, but it is generally a very interesting situation for how you... Generally, proving out that algorithms work is really important in situations like this. But getting an actual formal proof here isn't something that we can really do. We haven't defined it formally. We'll do it kind of close to that, but it isn't something extremely direct. So, the way we will roughly talk about this is, let's say at some stage of the computation, we have some set I of indices. This determines a lot. This determines a lot of the group action on the cosets. The thing is that this isn't a full action. We will call this as it is called in the book, a partial operation instead, or a partial action, in the same essence that a function which only is defined on a subset of a set that we are mapping from is called a partial function. There are effectively two kinds of steps we can do at any stage. We start with the indices being only one, being the subgroup H. We have two possible steps at any stage, really. One of the rules that we defined above, meaning we have to have a permutation, we have to have the trivial operation on one using the generators of H, and that relators have to act trivially. One of the rules gives I equals j for ij in our indices, or part 2. We choose a generator x and index I such that ix is not defined yet. And we set it to a new index, ix equals j. And then we append I with j. The process stops when we have an operation that is completely consistent with the rules we have done. It can be shown that the process terminates if preference is given to the first kind of step, where we equate things if the rules give us everything. We will not prove this, as that is quite hard. Instead, we will prove that if it terminates, we have something correct. And that is ultimately more important. This is theorem 9.10 in the book. So, suppose a finite number of repetitions of steps 1, 2 gives a consistent table. Consistent in this case meaning entirely compliant with the 4 rules that we have given earlier. Then the table defines a permutation representation which is isomorphic to the representation of cosets. This is the ultimate goal here. But we will need two lemmas very quickly to be able to actually do this. We will go into them as needed. So, we let I star to be the set of the final set of indices. We define a map phi star from I star into the set of cosets that, as earlier, I will be denoting as G quotient H, despite the fact that a proper quotient doesn't exist. This is done inductively. So, first of all, phi star of 1 will be H. Then, given a set of indices I at some step and a new step is done, creating, and a new step is done, either in the second step, in the second case, we extend via setting, we extend it via the rule that phi star of Ix has to be equal to phi star of J, where J is mapped to some coset. In the case of step 1, we need to be a little sneakier. So, in this case, we collapse. In this case, we collapse I to some new I star. To some new I prime, actually. One moment. Where, if we had phi of I into the cosets, we define a new phi prime from I prime into the cosets, such that if we have not collapsed K into something else, phi of K is equal to phi prime of K, and nothing new happens. If instead we have that I is equal to J determined, we set phi One moment. We set phi of I to be equal to, well, in this case, we set it to be equal to phi of I of j, which is equal to phi of I. So, we now need to prove that, in particular, part 1, we need to prove that this is compatible with the partial operation at every step. But this is given to us essentially immediately because we are setting it to be the case using step 2 whenever we are extending the function here. Continuing, we need a lemma specific to proving that part 1 actually works. And step 1 extension works. So this has a very hand-wavy explanation in Artin, which is essentially the operation on the cosets does actually work with everything here, does actually work with all of the rules, and therefore so must phi that we've constructed at every single step. This, because we are defining things via the multiplication cosets over here in part 2, whenever we are extending via step 2, this must work as needed. If the rules force it, then our extension also works as intended. Now, the last bit is a little harder to understand why we're doing this, but this is a separate lemma that is used in the rough proof-ish thing that we're doing here. So, we let S be a set acted on by a group G. We let S be an element of the set big S, stabilized by a subgroup of G called H. Then there is a unique map which we will call psi, that goes from the set of cosets of H and G into S, which is compatible with actions of G on both. In this case, we mean the action of left multiplying on cosets and left multiplying elements in S by G, because S is a subset of G. Well, S can be S is also acted on by G. And we also require that it sends that phi of H1, or 1H, generally of the coset, just denoted H, goes to S. So, if some of you have been present during the presentation about Chapter 5 in Artin, this will be extremely familiar. So, if we look at the action of G on cosets, G sends H to HG. So we are forcing psi of HG being equal to psi of HG, wherever G is outside. So, therefore, we must set psi of HG to be equal to SG. This gives us uniqueness immediately because we have no other way of defining the map. But we need to prove that it works, first of all. Let's say HA is equal to HB, the two cosets. But that immediately implies that BA minus 1 is inside of H. Hence, psi of HA is equal to psi of HA, which is equal to SA. And then psi of HB, which must, when psi of HB is equal to psi of HB, which is equal to SB. However, notice that because we have that BA minus 1 is in H, this, in particular, must give us that this is equal to S. Therefore, the action of BA minus 1 on the other set must be trivial. But that means that SA is equal to SB, and we are done. Now, this is where things get very funny. The point is that we now want to prove that our map phi star is bijective. Notice that phi star goes from our final set of indices into G quotient H. But what we can do using the lemma above is define a map which goes in reverse. And in particular, this is a good candidate for an inverse of phi star. If we prove that it's bijective by proving it has an inverse, we are done. So, we need to consider phi star, psi star, and psi star, phi star. If both of these are the identity on the respective sets, we are done. So, the way we do this, in particular, is because both of these are compatible with our group actions. Things get decently quick. So this goes from indexes to indexes, and this goes from cosets to cosets. So let's say we plug in H itself into psi star, phi star. Well, this has to map it to the index 1. But if we pick S, if we construct psi in such a way that the S that we picked over here is 1, well, this is H again. Similarly, in the other way, if we pick 1 over here, this has to be, phi star of H, which is again equal to 1. And we are done, as these are inverses. And this proves that we have a bijection. And everything is nice. Because if we have a bijection like this, our entire map is well defined. Our entire map from the cosets into the set of... Our entire map from the indices to the cosets is bijective, so we can treat them as one and the same. At least the action on both we can treat as one and the same. And we are done, and everything works as intended. If you want to see a proper proof of this, I suggest you look somewhere else. I have not been looking for this, but I'm pretty sure there is a direct proof somewhere. I'm going to look for it now, as we have a little bit of time. And I will post a quick... I will post a link to this in the chat over here, if I can find it, of course.